All right, let's get started. Okay, let's get started. Sorry about the glitch. So just somehow couldn't get the screen show up there. All right, so we talk about, before the exam, we talk about superposition, right? So when you have a beam that under multiple load, and then to find out the deflection of a beam under multiple load is you're looking for the solution of individual load. Right? For each load, what is the deflection you're going to get? And then just add them together. So if we put as a, like an outline, the theory, basically say, okay, if you have load 1, you find the deflection generated by it, that's the V1. And then if another load, you find the deflection generated by the V2. And then for the situation with 2 loads, you just combine them, add together. That's it. So the principle is really simple, right? You just add them together. If you have 5 load, 4 load, you just do the same thing, add them together. So that's the basic theory, right? And to make it easier, actually, we're going to show today a couple of examples. For each individual solution, for the V1, V2, you actually don't even need to looking for it. You can do it in advance, right? And prepare it, and then when you solve a problem, you just find the solution from it, and then you combine together. As I mentioned, in the textbook, they actually provide us with this. Let me just show this one here. So the textbook actually provide this table. Okay, so if you look at the back of the textbook, they give you this detailed table for simple beam or for cantilever beam. They give you all the loading condition. What the deflection will be, right? And you can find the basic solution from here. Right. So let me just pick any one, just go through, just explain what's actually available here. So let's say for a simple beam, so if you can make this a little bit bigger again. Okay, so for example, if for a simple beam, right? So here is a notation. So they explain to you all the, the variables they use. Okay, so basically you have the length L, right? The theta A, theta B, and then you have the deflection. So there's this table actually explain everything to you. Okay, and then for given situation, for example, if you have a distributed load, as you can see here, right? For this one, they give you 3 things here. Okay, one is I would say maybe 4 things. So one is they give you this V expression. So that's a general solution Vx. So you can, for any point, the deflection you can find from here. So that's the Vx, right? General solution. But this one always applying for any point. But many times, remember, we always try to find the maximum, right? So therefore, this solution also give you the maximum. You can see here, there the maximum is actually at the point C. Where is the point C? In the middle. So they say, okay, the middle is the maximum deflection. And they actually calculate this one, 5/384. Remember, last time somehow I memorized it correctly, right? So they give you this maximum value. And that is actually when you put x equals half L, you'll get this solution. Right? So that's one, 2 pieces of information. Also, they give you V prime. That's the angle at any location, right? Along this beam, any location, what's the angle? You can use this equation to calculate. And to that, they also give you at the boundary, the point A and the point B, the 2 ends, what's the angle of rotation there? Okay. So therefore, if I give you a problem, a simple beam, ask you to find out the deflection of any point, you can use the equation. Or I can ask you the maximum, you use the, of course, you don't need to go through this again, right? The easiest way, just use this equation. That's the maximum. So you don't need to do that calculation. By that, you save a lot of time. If I give you a problem to solve in homework or in the exam, if you just use this equation to find the maximum, it's much quicker. It's already given there. So you don't try to use this equation. So basically for you is make sure you know which one of the equations give you the answer quickly and use that. So if I ask you angle, you just use this one, right? Point A and point B, that's the angle. So you don't use this one to put the x value there. But somehow if I ask you when x equals to 1/3 of L or x equal to 1 meter, what's the deflection? Then you have to use this equation. That's a specific point, general point you have to use. Okay. So basically, you just need to understand what this table, what all this means, and then which one to use when there is a question. Okay. And then this is for distributed load. Then similarly, they give you for halfway distributed load, and they give you halfway distributed load, right? This one actually not halfway, just up to A portion, right? The B portion don't have it. Right. And then also, for example, there is a concentrated load in the middle, or if there is a concentrated load somewhere not in the middle. And then you have two load, that's a pair. So if I give you this situation, you can just come here, find the solution. Instead of using this one, do it twice, or use this one, do it twice to do the use superposition, find the solution, right? You can immediately, directly get the solution. So therefore, this will be the judgment for you. You know, which one fits to get your answer quickest. Right. So if I give you a pair of load, the same value, equally distributed, you just use this one. Okay. Similarly, if there is a moment on one side or moment in the middle, right, and or if there are two moments there, so two moments there, you can get solution, or distribute load or not uniform distribute load there. So basically, they give you all this basic solution there. Right. So if I ask you, give you a problem, you just check this table, say, oh, is the solution available? Right? If not, then you figure out, break it down to some of the basic situations that you use. Okay. So that's a general idea, how to solve for deflection or maximum deflection or angle using superposition. All right. Okay. Any question about this approach? All right. If not, let's just use a couple of examples just to say how can we use this table quickly find our solution. All right. Okay, so first example is this example. Actually, we went through this using the other approach, right? You do the integration okay, so for this one, oh, sorry, I forgot to switch to back here. Okay, so for this one, remember we solved it before. Now, if I ask you, I change the question, the same example, but I change the question. I ask you, okay, so point C, going to be the maximum deflection. So I just give you one question. What's the maximum deflection of this beam? I just care about the one, okay, what's the maximum deflection of this beam? Okay, how can you find the solution? Use superposition, right? All right, so superposition. So you find the solution for this one. And then you find the solution for this one. Right? You add them together. So those two add together give you the answer. So you find the maximum for this one, maximum for this one. All right? Okay, can we find the maximum for each one of this? Yes. All right. So we actually did this before the exam. I just want to review it, make sure we still somehow remember it. Right? Okay, so if you look at the table, actually here, let me switch to this one again. Okay. All right, so if you look at the table here, you have this, they give you the maximum deflection, right? So for distributed load, that's the value. And then for this one, okay, so if you look at for this table, okay, which one should you use? They give you a couple of things here. Which one should you use? Just to take the maximum, right? Because that's what you care. That's the question. So you just find this one. So basically this part plus this part. And that's it. That's the answer. Right? So it's easy? Very easy, right? It just take a little bit of time punching the key, punching the numbers to the calculation. But the method-wise approach is really straightforward. You just add them together. Okay. All right. So now let's just go over to a different problem here. Okay. So here's a different. Let me switch back. Okay, so here's a second example. Okay, here we have cantilever beam. And there are two loads applying there, or two types of loads there. One is a constant force at the end. One is a distributed load, Q. Okay. How can you find out the maximum deflection of this beam? The question is maximum deflection. Okay. Where is the maximum deflection? At the end, because you have the cantilever beam like this, right? When you press on, always this far end move the biggest distance, right? The deflection will be the biggest, or maximum deflection. So basically, the question is, what's the deflection at the point B under these two loads? All right. Okay, how can we find the answer? Looking for the table, right? Okay, so now we have to switch back again. Look at the table. Since many of you don't have the book, so I'll just switch back so you can see here. All right, so if you look at the table, which one we should look? Is this the right page? No, this is a round type of beam, right? So we need to go find, oh, here is a cantilever beam. That's what we're looking for. Okay, cantilever beam. Now if you go through this table, okay, so here, okay, it's a start here. All right, so explain everything, give you delta B, right? You see there, for example, here, they give you delta B. Okay, is this the one we need? No, because this is all the way through. Is this one? Yes, this is the one. Okay, so now if you look at this one, okay, what they give you? They give you V at X 0 to A range. Okay, and then they give you the V prime there. Also, they give you V for that range, right? And then they give you this at X equals A. What's this one? All right, and then they give you delta B as well, right? So which one should they use? Delta B, because you're looking for delta B. That's the question, right? So therefore, we use this delta B. Okay. All right. So we have the delta B. Let me just write it down, copy it down here, so we can use it. That is 24. So QA for 24 EI, and then inside will be 4L minus 8. All right. So we have this from the Q. Okay. Now keep looking for the table. All right. Where is the other solution? Other part of the solution. Number 4. Okay. So number 4 here. They give you this multiple things here. Now again, which one should we use? Delta B, right? So delta B, that's what they ask you. Okay, so delta B, that's a 3. Okay, PL cubic. So PL cubic over 3EI. That's it. Okay, now can you find the final answer? Yes? Okay, so just add them together. That's it. Too easy, huh? There's not much trick there. Just pretty straightforward. You just add them together. All right. Okay. All right. Let's go over more example here. Okay. Actually, before I move on, I want to ask you how did they get this solution anyway? That idea. If we look at this, let's look at this part again, because we're going to need this idea later on. So I want to show this. Okay, look at this answer here, right? They give you this answer. Okay, how did they get this answer? Okay, so if you look at the front one, if you have a beam from 0 to L, they give you delta B, right? For this one, they also give you delta at the point A. So delta A, where is delta A? Here. At X equals A, V equals that, right? If you compare this one, see it's the same equation. Now, from this one, how do you get this delta B? What's the relation between delta B and this delta A? Or delta middle? What's the relation? Okay, So here is just one quick hint here. So if you have this beam, right? So the beam, you have this load applying here. Thank you. All right, so you have this beam, and the load is only this range, right? Now imagine if you just look at this part of the beam, the left part of the beam. That's pretty much like a cantilever beam with the load all the way through. So you can use that equation from above. You get the deflection of this part. So you get this delta, call this point C, right? Okay, now how does this point move? You will move along with this point C, right? So you will move here, but actually you're going to move further. Why? Because this beam, this part, after this point, it will remain as straight, right? So where this straight line is, it will be this angle. It will be this angle at point C. So whatever the slope at point C, it will remain as that, go all the way down here, right? So this part will remain straight line. So therefore, one way you can find how much this point move is find out how much this point move, and then you add this triangle, and that theta is the delta C, and that value is given. Okay. So sometimes we need this trick a lot. For example, if I give you one example here. Okay, let's say we have a beam. Right? That is, what do we call this? Overhanging beam. Right? So if you're applying load here, then if you want to find out what's the deflection here, you basically kind of figure out, okay, how much this point move, deflect, and then at this point and this angle, it will go straight because there's no load on this portion, so there's no further bending. So the beam will remain straight. That's one situation. Another situation, for example, if you have a beam like this, so you're applying load P here, you want to find out the deflection here. Delta at point B. Okay, here is this point C. How can you find the deflection at the point B? You use this, let's call this O. So OC portion. So the OC portion, this part will be deflection, right? So we'll deflect something like this. And then follow this angle. There's no load, so this will remain straight line. Right. So the part, the stand free, no load, it will remain as a straight line. Beam will remain straight. There's no bending. Right. So, and you base on this slope here. So this distance plus this slope, this angle, and give you this. So this is a trick we use pretty often. That's why I want mentioned here. All right. Okay, so let's go to another example. Okay, you want to go through a simple beam or cantilever beam? Pick a beam. Cantilever. Okay, so let's do a cantilever beam. Okay, let's say we have a cantilever beam. All right, gives 2 or 3 loads.
20 pounds.
20 pounds where?
At the end.
At the end. Okay, so here we have 20 pounds. How about we have another 20 pounds somewhere, or another load? Give a value.
10.
Something 15? Okay, let's say we have 15 pounds here, or 15 Newton, right? Like international unit. Okay, so beam we know here's 3 meters long. Here's 3 meters long, and we know the EI value. So we know the cross section, the material modulus. Okay, and okay, what do you want to find out about the maximum deflection? Right? Or put another way, we want to find the deflection, the point, and this one we call it point C, and this deflection at point B. So here's point A. Okay, so here is a beam. Right? And the 2 loads. What's the deflection at point C, deflection at point B? Then we can compare which one is maximum. Right? Okay, can we find a solution from the table? If I can find a solution, then I don't have to solve it. Right? Okay, so look at the solution. So here is the table they provide to us. The first page, second page, all right? And then third page. Anyone found a solution? No? Other page? Before
Page 1042.
this page, there's no two loads applying there. So they give you individual, right? So 4 and 5. Yes, you already found the way to solve it. Combine 4 and 5. That's it. Okay, now let's do it this way. So basically, that means we change this problem into two problems. One is you have a beam. Okay, here you have a 15, right? So let's call this P1. P1 equals 15. Another one is this load here. You have this. Oh, sorry. Keep forgetting. Okay, so you change this problem, break it down to two problems. One is a load P1, 15 at the middle. Another is a load P2 equals 20 here at the end, right? Because we want to use superposition, so you break it down to two problems. Okay, now for the first one, can we find out the delta B and the delta C? And for this one, can we find out delta B and delta C? I'll call this prime, right, from the second one, and this from the first load. Or you can use prime. Anyway, notation will be fine, as long as you explain, right? Okay, so for the first load, P1, what's the delta B? We can use table the number 5, right? Okay, so number 5, I need my glasses. Okay, I'll just copy from, imagine I'm checking to copy it correctly, okay. So for this one, delta B equals to, okay, so equals to, that will be PA squared, then 6EI, okay, and then 3L over 8. Okay, let me quickly show you what I'm copying, then you can check whether I'm copying it correct or not. Okay, here's the solution. Am I copying it correct? Okay, switch back. This equation. Am I copying it correct? I'll say yes, but I also you can say no, because see, look at this one here. They give you delta B, right? I'm writing as delta C. Am I correct? I'm correct, because B point is here. That's the notation here. And for my notation, I assume this point B. So, right? So what I did wrong? I call this B. They call this B as well. So if I put C here, I'm wrong. So this should be B. Right? So I did copy it wrong. See, which one? Point B is this end. And that's the same notation in the book. They call this point B. Okay. My point is actually really easy. Make sure which point you are trying to find the deflection. And that's the point they give you. So it doesn't matter which letter you call it. You can call this point W point or X point, Y point. Right? Just make sure where you look at. Okay, so for this one, we look at the end. So for the end, we have this one. Doesn't matter for which load, for which one. See here. Let me coming back to this part. So unfortunately, we don't have somehow can show both screen. It's not true. Okay, now look at it. So this point B, right? Point B is the very end. So the force is the middle. So I'm copying the correct. I selected correct, right? I selected number 5. That's correct. Okay. So now from here, if you look at the point A, okay, that's a deflection. So PA cubic over 3EI. Okay, so PA cubic over 3EI. All right. So this point should be PA cubic over 3EI. Right? That's the middle point, the A point. All right. So I'm copying it correct, right? Okay. Now, if you look at for this one, for the second one, for this one. Okay, what's the delta at point C. We call this one B. This is B. This is supposed to be C, right? So middle point is C. End point is B. Okay, for this one, now let's switch back to the table. Okay, we know we should use number 4, right? So number 4 is the one we're supposed to use. Okay, now this one gave me delta B equals PL cubic of 3I. And that B point is the end, right? Okay, so therefore, let's say I need to write down here, the B point is 8. So it's 3EI PL cubic. I write down there. Okay, now, actually I need to switch to show you what I wrote. Okay, so I wrote down delta B. Now what about this delta C? How can I find the delta C? For a cantilever beam, there's a load applying the end, P2 applying end. How can I find the deflection here? Let's look at the table, right? So look at the table. Okay, look at the table here. Okay, this table, it didn't give me the deflection of the middle point. Now, how can I find that? Use the general equation, Vx, right? So put it here, you put the x equals half L. Right? That'll give you the value. Yes?
If you find the deflection at point B, could you just use the triangle on the deck?
Okay, good question. Okay, now let me switch back here. Okay, the question is, now we know this delta B, so we know how much this point is going to move. Can we use a triangle to find the delta C here? Any comment? Yes? No. Why is no? It's a curved beam. It's not a straight line. See, imagine you bending that beam. It won't be a straight line. So there's no triangle there. That's not like in chapter 1. Remember we talked about there is a pin support there. So this thing remains as straight when they move. So therefore you have triangle. Here, you can never use triangle because the beam is curved or become curved. Right? Okay, so that's an easy answer question. Right? All right, so we can now use that. So we have to use the Vx and let the x equals to half L and give you that answer. Okay, if we plug this in, okay, let's look at this table here again. Okay, so let me write down here. That one, the Vx is actually equal to, I'm just copying here so we don't have to switch the screen. Okay, equals px squared and then 6EI. And then will be 3L minus x. Okay, that's a general equation for this part. For this part. Okay, now we just plug x equals half L in there. You'll get the solution. Yeah, negatively going down. Yes, it's supposed to be negative.
Where are we going to use this negative? If the images have the P pointing down. Wow.
Good point. That's the next point I'm trying to bring up. Okay, if you look at this, okay, look at the table again. We need to look at the table again. All right. So if you look at the solution, number 4 and number 5, right? That's what we're interested in. Okay. So in number 4, load is pointing downward. So you have deflection that point this way. Everything is assuming the load is downward, right? This one, assuming a load is pointing downward, they'll give you the solution. You can directly copy there, right? Now, if you go back to the problem we have here, okay, this one, yes, downward, P20, right? P2 equal 20, that's downward, so you directly use it. Now, what about P1? It's going upward. Now, the table give you this solution. Now, how do you use this solution? You see, this one assumes the P point downward. So therefore, how you get the solution for this particular problem, for this problem? You just use the negative value. Just change everything to negative. So therefore, when you add these two together, right? Remember, we're trying to add these two together. when you add them together, actually the value, they're minus each other. So therefore, you should put p equals 15, right? So this p value, you put a negative 15. Or you can say it's supposed to be negative p, so negative 15 here. And that's it. And this one, when you put the p value, it's positive 20. So here your p is equals positive 20. Right? And so that's the only thing when you use the formula. Pay attention which direction is the table assumed the direction. Which direction is the problem giving direction. If they're consistent, use it directly. If not, change the sign. Just need to be careful. That's it. All right, you have a question?
The direction of the negative.
Yeah, for the formula, you search from the table. For upward is negative because they use a sign that assume p is downward.
Deformation will always be after that.
Well, the deflection, well, that's actually because we call, if you have this load, if something moving down, we say that's a positive deflection, right? So therefore, the value going down will be a positive value deflection. But if that one going to move it upward, so therefore you have a negative value.
Does the 20 over power 15 is kind of like S curve?
Which one you talking?
Sort of like make an S, go up and then down, or is it just
Yeah.
20
For this one, it most likely, okay, this is going down, but this 15 is comparative, right? So I think it will go up a little, then go down. And for actual one, depending on this P1, P2 value, can be all different shape. That's why when I ask you, where is the maximum? You have to check point B and check point C, see which one actually is the maximum. So it's hard to tell if I don't know P1, P2 relative values. The easiest case is P1, P2 both point downward, then they all go down, push it down, right? Or P1, P2 all go upward. That's the easy case. So if P1, P2 opposite direction, so it can be one part of the beam going up, one part of the beam going down. So you have to depend on the values. Okay, so in summary, I would say this part of the problem, the approach is really easy. The only part, you just need to pay small attention to, the sign, to the calculation, and that's it. But the problem is pretty straightforward. Which is
So get more equations for two diagrams.
Yeah, so what's next? His question is basically, what's the next? Give the answer. Okay, what's the question we're asking? The deflection of the point B and deflection point C, right? So what's next? You just add them together. Add them together, give you B, give you C, right? And then you compare them, which one is the maximum. All right. Okay, any questions? All right, if you don't have a question, I want to ask you a question. Okay, let's say I have this beam. All right, and I have a load applying here. Start from the middle, end to somewhere. So I know all these locations, right? Where it start, where it end. Okay, I want to find out the deflection or the maximum deflection for this beam. So I know the Q. Oh. See, this start from, let's say this part 4 meters here. Maybe make it easier. Here is 6 meters. So this part is 2 meters long. This part 2 meters long as well. Can we find the maximum deflection of this beam? Can you find the table? Let's check the table. If there, that's perfect. We don't need to do anything, right? Okay, look at the table. Let's look at it together. It is?
3 and 2.
Okay, let's say 3. No, 3 and 2. Not sure. So this one, distribute load. That's half all the way to A, right? But not start, this one, what we have is right in the middle, not starting from the end, right? So there's no solution there. Right? See here.
If you convert it to look like
See? I'm not cheating you, right? There's no solution. Why are you laughing? There's no solution directly given there. Right? See, they don't give you that solution. subtract. That's the trick, right? So you can basically say this problem equal to this problem. Oh, equal to this problem, and then plus. Basically, plus means minus, right? Okay, minus this problem. Yeah, plus equals minus means minus, right? It's algebra. It's not just a positive number, right? So you add these two together, subtract them together. That's adding, subtract. That's the same thing, right? Well, they both have solution there, so you can find it. Yeah.
Can you make it a concentrated load and figure that out?
Yes. Okay. Another approach he just mentioned. Instead of I'm doing this two minus each other, okay, I can fill this one. Okay, I'll say this is equal to, okay, this situation. There is a small load Q dx here. That's a constant force, right? Then I have another one. There's small load. This is start from, this is the x equals, this is 4, right? So then this will be 4 here, and then this will be small. This will be a d. So this is another q dx at the location. This is x distance. There are many of this. So I can divide into many small load, add them together. What does that mean? Integral. Right? You can do this way as well. Okay. But you cannot do this way. Say, I'll find the solution, a concentrated load here. Find the deflection. You cannot do that. Because this load is different from a distributed load. All right. Okay, but you can do this. Do all the integral. So for the q dx, you find a small dv, the v, and then you do the integral. Okay. Now, which way is easier? The first one, right? Because this one, you have two solutions already given. You just multiply, or subtract each other. Right. So when you have a problem, there are multiple ways. The easy way, use that. Right. Okay, now, what if you have this situation? The beam, you have a concentrated force, a moment, and then you have a distributed load. Okay, can we solve this one? Okay, how do you solve it? Divide it up into 3 different, and each one actually, fortunately, there's a solution there already. Right? Okay, now what about this one? Let's say I give you one problem here. Let's say I have 2 load P here. And then let's say there's a distributed load here. Okay, how do you solve this one? You divide up. How do you divide it? That's my question. You change this one to how many problems? 3, right? P, that's 2. And the distributed load. Yes, you can change to 2. Which one quicker? Easier? You divide less. You divide into 2. That's easier. So you would divide this into a pair of load there, and you can find a solution right away. So let me show this again. Okay, so you would divide into a pair of load. Oh, right away you find a solution. And then you divide into the distributed load, you find the solution. So this is much quicker. Less calculation, faster. Right? All right? Okay, any questions? If not, try to do the new homework. All right? We got Yes.
I got you.
Yeah.
I have no idea why we use the delta B here and delta C here. Why we use the delta B, both of them, for the first one?
For the first one?
Yeah.
Okay, for this one. Okay, you want to find what do you want? What are you looking for? You want the deflection here and the deflection here, right? Okay, deflection here they give you.
So,
Yeah, see, they give you. No, this one is different. You're looking at the wrong one. Yeah, this is the one. So they give you delta B. So you know this point. And also they give you this point. So you know this two solution already for this load. You know this deflection here, deflection here. They give you. So this is delta A. This is they call delta X equals A and delta B. Right? So they give you. And this one they give you only the B point, this point. So you don't know what's here. So therefore you have to use this equation to let X equals half L finally.
thank you.
So you said when they point down it means positive, when they point up it's negative.
Yeah.
So like when this equation has a negative in here, right?
Mm-hmm.
I mean, it's because it's pointing down though.
Yeah.
So if it's going pointing up, then it'd be positive.
Yeah.
Okay.
So basically, what they have here, okay, this is equal.
This is negative.
Yeah. So this whole thing, remember that when the load is here, remember that our coordinate is y is going this way. That's the positive y.
Right.
That's why all the deflection here is negative. Yeah. The reason they call delta b, once you have delta b, it's still negative, right?
Right.
But they say that's the value.
Positive value.
Yeah, that's the scalar number. There's no sign.
So for this p, then I would use a negative p or a positive p still.
Well, if they say p equals 20, so you should put 20 here, 20, positive 20, 20.
The p, alright, so if the p was going up, then would that be negative?
Then
p?
you want to put a negative there.
Why? If it's an
In
angle.
real problem, if you have only one load, it doesn't matter. You just say, okay, you'll go up 1 millimeter or down 1 millimeter.
So depending
it's
on-
only when you have multiple load, then they are saying you need a consistency.
So you're saying the coordinate system for the v and the coordinate system for this one is opposite?
Because this is different. They use this one actually, I won't say that way. It's actually, for this one, they have the y coordinate. Because it's v, like a displacement,
Right, so
direction.
so y is positive.
Yeah, this is like the absolute distance.
Yeah.
So therefore, there's no negative. Doesn't matter which way. That's the maximum distance.
So you could just put a positive number, then you just have to know if you have to subtract.
Yeah.
Okay, that's fine.
Yeah, that's it.
Have you had a chance to look into that class, that test over the summer? Or
Uh,
I emailed you and spoke to you about it.
Yeah, sorry, I haven't.
You didn't have time?
Yeah, I haven't looked at it.
Yeah.
Okay, let me remember. I'll talk to the person.
Okay.
I'll try to. Maybe actually it will be helpful if you don't mind. Shoot me another email. I'll
yeah.
reply. Other than I have to go find your early email.
All right.
Okay.
Thank you.
I'm so confused about it. So we want to find the delta B.
If
and
you don't
delta C.
hear back from me, ask me Friday. I can give you your answer definitely by Friday. Alright? Okay.
So we want to find the delta B here and delta C here, right?
Yeah, that's what you call. You can call this B, this C. That doesn't matter.
Okay, so if we call this C and this B, we separate these two loads together. We separate them, right? And we go to the
Yeah, so
table.
it's a superposition. So you divide this problem has multiple load into one problem with one load, another problem with another load. That's it.
So this point is called C and this point called B, right?
Yeah. So for point B, they give you solution. The book give you solution. Right? See here, they give you B solution.
Is it for this B here or for the point
No,
C?
for B. See, you check here. Look at this one. They tell you where is the point B. If you look here, okay. See, B is here.
Okay, so
You look at this table. They give you explanation what they use, the sign they use here. They don't care whoever uses what sign. For this table here, they use this sign convention. So, okay, so that's the B point.
So for the delta B is gonna be here at the end.
Yeah,
For why we form the delta B dash? I mean
because this
down-
one called delta B, this one delta B down. That's the reason. So, because this is one load, this from P1, this from P2, so that's two different loads. You have to add them together later on. Right? All right.